One of the great benefits of being in the field here at Lassen Volcanic National Park is that we can see all the forces that contribute to form the wonderful environment that's here. And specifically, we can see how the geologic processes of the Earth, for example, the volcanic activity that we see here, interact with the water that we have at the surface and the other aspects that determine the local climate to give us the plants and animals that are very much a part of Lassen Volcanic National Park. And so this talk really addresses these major forces of nature that come together to really shape the environment and the organisms that live within it. Well, the one great way to start with this process is to look at the source of the heat that really gives power to the volcanoes at Lassen. And that is to talk about the composition of the Earth itself. Clearly we have the water and the atmosphere with its nitrogen and oxygen, but we have the rocks and the deep interior of the Earth also that play a very important role. In addition to the elements that make up the rocks, such as silicon and oxygen, sodium and potassium and magnesium, calcium, and all of those, there are also other elements that are much heavier, and these are radioactive elements, specifically uranium, thorium, and one of the isotopes of potassium, that are decaying and generating a large amount of heat. Now, the interesting consequence of this is that the interior of the Earth has become quite hot. And this is not only because of the heat that's produced by uranium, thorium, and potassium-40, but also because the Earth as a material is not a very good conductor, and so it has to get very hot on the inside before that heat finally gets to the surface and escapes. Now, there are large temperature gradients, and that is to say the interior of the Earth is much hotter than the outside, and this can be a useful source of energy. For example, at the lower left you see what we call a geothermal power plant, which uses deep wells into parts of the crust that are very hot to bring steam to the surface and to drive wind turbines from which we can get electrical energy. The interesting aspect about this radioactive heating of the Earth is that we basically use the same principle in our nuclear power plants. Only in this case we take some of these elements that are radioactive and re-enrich them. We concentrate them very much in order to cause a very intense source of heat that we can then use again to heat water to steam, take it over to an electric power plant, and derive useful energy. So it's rather curious that whether we are using geothermal wells, as you see on the lower left, or the nuclear power plants that of course are quite well known to us all today, we're basically utilizing the same principles of nature in both cases. Radioactive decay that gives rise to heat, which in turn can create steam and then drive the generation of electrical power. The interesting twist, of course, is that we are not only using these useful sources of energy on the Earth from radioactive decay. We have a radioactive source on our Mars rover Curiosity, which is used to heat an electrical device that again provides power to the rover. So in a way, the very radioactivity that drives the geological processes of the Earth has become quite useful for a lot of things that we do as a civilization. And so let's talk a little more now about how this heat that's produced deep within the Earth actually shapes the architecture of the Earth's crust and therefore the environments in which we live. The ocean basins on the Earth are sort of what we call the global lowlands, and of course that's where all that seawater is. But the floor of these oceans is a huge volcanic province in itself. The entire seafloor is very underlain by volcanic rock that has erupted along what we call the mid-ocean ridges and spread apart to create the ocean basins as we see them today. Now when these spreading seafloor areas encounter continents, there's a collision as shown sort of in the lower right here, where the ocean plate goes beneath the continent, and when this happens it creates another spot where a lot of heat is generated and rises to the surface. And this of course is the heat and the molten rock that we associate with volcanoes such as Lassen Peak and some of the others that you see indicated in the upper right image. And so the same heat engine that generates so much of the landscape of the Earth is directly responsible for the volcanoes that we see at Lassen, and therefore this geologic heat, this source of energy for volcanoes, is a very important part in the landscape of Lassen Volcanic Park. So the particular field site that we are visiting in this course, Warner Valley, is shown in this white oval that you see at the lower right center of this image. And at the upper left is Lassen Volcano, sort of highlighted by the very light colors that you see, a combination of snow and very light colored volcanic ash. You can see in the upper right an image taken in 1915 of the eruption of Lassen. And just to underscore again that when this heat from the interior of the Earth comes out, in certain places, such as Lassen, you can get some very dramatic events. So a lot of the light-colored ground that you see in the upper left of this image, the main image here, sort of delineates the lava flows and ash flows that have been part of the activity of Lassen Volcano in the distant past. And you can see that our field area there in Warner Valley is just off to the southeast of these most prominent lava flows that we can see today. Here is the view as if you were, and again from Google Earth, if you were flying in an airplane just approaching Lassen from the west, flying towards the east and looking down slope to the east towards the Warner Valley field area, again highlighted in that oval. And you can see the lava flows just sort of coming down off of the volcano, again those lighter colored areas, indicating that really the whole Warner Valley area probably sometime in the past has been affected by lava flows and activity, much as you see in the foreground. And of course, just for perspective, you see Lake Almanor off in the distance, and Chester located just beneath the letters Lake Almanor, that of course we drove through on our way up to the field area. So anyway, this is sort of the view from the volcano, highlighting some of these lava flows and volcanic activities that have happened in the past. So this is the volcanic aspect of Lassen Park. And just to highlight a little bit what it might have looked like when some of these flows occurred, here's an image, or actually a movie taken from Hawaii and the Big Island, just showing you what some of the lava flows look like when they're actually happening. In the case of Hawaii, you see the actual fountains that are associated with the lava flows, and of course that makes it all the more dramatic scenery. But there are places actually in the northeast corner of Lassen Volcanic Park where you can see some very fresh examples of cinder cones and lava flows, and we'll actually be seeing those later in the course. So again, similar processes as in Hawaii, and very much important in shaping the landscape. So now here again is our field site, Warner Valley, and now the oval is blue in color, but it delineates on what we call here a geologic map the general area where the valley is located, where we're doing our field work. The principal point of showing you this slide are all these colored areas. And each of these colored areas represents some kind of a volcanic flow that occurred in the past. And the different colors represent the different kinds of rocks, which in turn represent different volcanic eruptions, and in some cases, rock having a different composition. And so the main point in this slide is that for millions of years, there have been lava flows and volcanic ash deposits being laid down in the area surrounding Warner Valley, and actually of course must be in Warner Valley also, that really come together to give you the landscape that you see. And particularly when we're in the valley looking up at the various mountains that you can see, they all represent the remnants of various lava flows that have happened in the past. And so this is now the geologic part of Warner Valley. This is shows a little bit of the history there that has gone into shaping the landscape that we see here. Okay, so that's a very important aspect of the geologic processes and the volcanic deposits that are part of the Warner Valley field area. Another major aspect of the Warner Valley field area and Lassen Park, of course, is what we call the hydrologic cycle. And of course, I'm sure all of you are familiar with representations of how the water falls from the sky as precipitation. It hits the ground and either runs off as streams or infiltrates into the ground to charge up what we call groundwater, which eventually flows out to rivers and lakes and ultimately the ocean. And of course then in those places it evaporates again, goes back up into the atmosphere and cycles back again to give us the precipitation on the land and of course out in the ocean as well. Of course Lassen is very much involved in this hydrologic cycle, as virtually all of the precipitation in Lassen occurs as snowfall during the winter months. And Lassen Park actually is a very important part of the water budget for California, supporting much of the agricultural needs in the Central Valley, for example. And so really the part of Lassen is to accumulate the snow at high ground during the winter and then let that water slowly be delivered to lower elevations as we move through spring into the summer. But the key part is that this hydrologic cycle is a very important additional story in Lassen Park. Here is the nice picture taken in the wintertime, just showing how much snow does accumulate on Lassen and the surrounding high ground. Part of that water budget, part of the sort of storage of water that we get by virtue of the Sierras and the volcanoes such as Lassen. And of course then during the spring and summer this water, this snow melts and begins to send the water back towards the sea. Again, the same view I showed you earlier, just to remind us that not only lava flows downhill, but water flows downhill, and so between the high ground you see just at the bottom of this picture and out there at Lake Almanor, we have water flowing both at the surface and in the subsurface. And both of these pathways for water are very important in understanding what we will be seeing in this Warner Valley field area. This is another view just now from the east, looking back west across Warner Valley in the near foreground there at center, out towards Lassen Peak in the upper right. Just again to give you a perspective of how the water probably moves in the subsurface as it moves from that high ground up by Lassen Peak, sort of towards you and maybe down to the left on its way down to Lake Almanor. And so what's the story of the water? As it precipitates, it falls from the sky on the high ground and then makes its way downhill. The interesting twist here with Lassen is that not only does water flow down along the surface and also flow through the subsurface as groundwater, but every once in a while at certain places it encounters a very hot zone. And this, of course, as I mentioned earlier, is due to the lava and the intense amount of heat that can be found in certain places in the subsurface in Lassen Park. And when the water encounters such a hot zone, it does what water does when it's heated. It rises. It becomes less dense, it expands, and as a consequence, it rises towards the surface. Now, if it rises slowly towards the surface, it can cool off and stay as a liquid all the way and to the top and form a spring. But in places where the water rises very quickly, sometimes it reaches a lower pressure where it begins to boil in the subsurface before it gets to the surface, and that creates, of course, steam, what we call the vapor-dominated zone, and you see at the surface steaming vents called fumaroles, and maybe in other cases where you've had a little bit of condensation near the surface, this steam will condense to form what we call the acid sulfate hot springs, and we'll talk about that a bit more. Here's an example of an extreme case where water is not only heated in the subsurface, but it gets to rise very quickly to the surface and flashes very quickly to create a very dramatic scene, such as you're seeing in slow motion here. Here you see the erupting steam plume bursting through the overlying water. You would call this a geyser, although it's what we call a drowned geyser because the steam has to move up through a standing water column. But anyway, it makes for a very dramatic scene, just illustrating the intense amount of heat that is coming out from the interior of the Earth, in some cases creating very dramatic features. We have a very dramatic feature of our own here in Lassen called Bumpus Hell, and this is an example of what I mentioned earlier, where the water is heated by this volcanic rock and lava in the deep subsurface. It begins to rise towards the surface and actually encounters lower pressure and begins to boil. And in the case of Bumpus Hell, the steam makes it all the way to the surface and to create this big roaring fumarole that you can hear and see when you go to Bumpus Hell. So Lassen has its own share of very dramatic features related to the water interacting with the hot volcanic rock and lava. A very important part of this encounter is that the lava and the hot rock contain chemical species which get into the water and the steam and constitute what we call the volcanic gases that come out. Well, the most obvious example of that, of course, is water vapor. There actually is some water in the lava itself in addition to the groundwater, which then comes together to give you that steam that you see. But we also have carbon dioxide and various sulfur gases, such as sulfur dioxide and hydrogen sulfide, that impart that very distinctive smell that we associate with volcanic gases. There's also other gases like hydrogen and a number of minor gases, which are indeed very minor in their abundance, but over the long history of the Earth have played a very important role in shaping our atmosphere. For example, the nitrogen and the argon in our atmosphere, as well as these rare gases like helium and argon and neon are very important aspects of our atmosphere, and they ultimately have derived from volcanic processes. The important point for our story here today, though, is that these chemicals, particularly the water vapor, the carbon dioxide, and the sulfur gases, they affect the reactions that can occur between rocks and water. All that hot water interacts with the rock, and especially at elevated temperatures, it creates solutes that are dissolved in the water that are very important for helping us understand the nature of that water and how it affects the kinds of life that lives in it. So these gases that are included with the boiling water are a very important part of understanding how volcanoes and water interact to create environments for life. One nice example, another place in the park, is Sulphur Works, and the graphic at left illustrates a lot of what I just said, and that is that the snowfall on the high peaks melts, the water gets into the underground, it drops down to a point where it actually encounters some very hot lava or rock, and of course is heated, it rises rapidly because of that heat, and as you can see going up on the right side of that diagram on the left side here, it gets to a point where it boils, and what we see at the surface are fumaroles, or in some cases mud pots. And again, there are gases associated with the lava that get into the water, and they become a very important part of the chemistry of the water that we see at these sites at the surface. And this is something that we'll be exploring here in Warner Valley, and that is the different compositions of the waters that we see and how that might relate to the kinds of organisms that live there. Again, showing the picture here of the water melting, moving into the subsurface, encountering these lava areas and hot rock areas, and then rising to give rise to the features that we'll be seeing in Warner Valley. Again, now we see a view of Warner Valley from Google Earth, again highlighted in the oval. You'll notice a light green area inside that oval, and that represents the meadow, whereas the more muted, darker green colors represent the canopy of trees that are also, of course, part of the field area, particularly on the slopes surrounding the Warner Valley itself. And as we zoom in more closely here, we see the campsite that the group has stayed at, and the meadow sort of as you move towards the left, and towards the left also is the route that we take on our hikes to look at various springs that are located around the margins of the valley, highlighted in that lighter green area, and then ultimately walking out to Devil's Kitchen, which represents another place where this heated water has come to the surface to create some very interesting features. And of course, an interesting question is, why are these certain features like Devil's Kitchen and Cold Boiling Lake located where they are? Well, of course, one answer is that there was water available in the subsurface. The second one is that there's heat available down there also to heat up the water and cause it to rise. But there's also deep fractures within the crust, within the rocks themselves, and these fractures represent passageways or conduits through which this heated water can rise rapidly to the surface, and by rising rapidly, it boils before it gets to the surface and thus creates a steam type feature. So you can see these orange lines here indicate places where geologists have located fractures in the crust of the earth, and they sort of complete the picture. They show us how the combination of the heat and the groundwater combines to create these features at specific places, and those specific places are determined by the locations of fractures that allow that hot water to rise very quickly to the surface. And so you can see how various aspects of the geology, the heat that's produced in the rocks, as well as the hydrologic water cycle, combine to give you the features that we see in the landscape of Warner Valley. Again, going back to the picture of the geologic map showing the different types of rocks, I show this again to make the point that the water in the subsurface, as it moves through these rocks, will interact with these rocks, and particularly so at high temperatures. And it could be that there is a relationship between the kinds of rocks that this water passes through and the kinds of chemicals that we see dissolved in the solutes in the waters that we will be sampling. And so then the question is, what role, if any, do the different types of rocks play in determining the composition of the water, and how might that in some way influence the kinds of organisms that we will find there? And so you can see now that the geologic aspect, not just the heat, but the rock composition itself, could play an important role in helping us understand the nature of life living in Warner Valley. And as we explore these ideas, we will be taking water samples, and they will be sent out for analyses. For a lot of the species that you see listed down on the lower left side of this diagram, and we will be analyzing these different elements at different locations, in springs that are alkaline, ones that have a more neutral pH, and springs that are very acidic, and to try to address the question of how does the precipitation, the snowfall, the rocks that we've encountered in the watershed, and the types of gases coming volcanoes from the volcanic activity interact with these rocks at various temperatures to create what we see dissolved in the water, and in turn perhaps influence the organisms that are living there. So these elements that are listed on the left will play a very important role in helping us understand relationships between the geology, the hydrologic cycle, and the life that's in Warner Valley. And again, just another picture showing a close-up of the meadow, where our campsite was over to the right side of the meadow, and we hiked through a number of springs, and many of these springs occur right where you see the boundary between the meadow and the higher slopes of the valley, both to the south and to the north. And that'll be an interesting part of our investigation. Here's a close-up again from Google Earth of Devil's Kitchen, showing very light-colored ground out there, and we're out there, and we're going to be looking at this and trying to understand all the aspects of this very interesting feature and how it plays into the story of geology and water interacting to create environments for life. And this is just an image from previous years of students taking samples and making observations at sulfur works, pretty much doing what we'll be doing here, and that is understanding the nature of the water and making other observations to explore these relationships. And then, of course, what this does is it gives us perspectives on the early history of our own biosphere. And that is to say, how has volcanic activity in its various ways interacted with water in the distant geologic past to create environments that might have been very supportive of early life. And of course, early life on the Earth was single-celled organisms, microorganisms, much like the ones that we will see at our various field sites. And so, in a way, our observations at our field sites in Warner Valley will give us perspectives about what might have been the nature of life on the early Earth. And since life on Earth arose perhaps very early in the history of the Earth, maybe the same thing happened on other planets. And so here we have an image of Mars, again taken from orbit, and that dotted circle you see in the upper center is the summit caldera of a volcano called Hadriaca Patera. The various sort of wavy lines, features that you see coming out from that in various directions represent the slopes of the volcano Hadriaca Patera. And on the southern slope you can see this large sort of feature that's incised in and looks like it's got something coming to the surface maybe and flowing out to the off the bottom edge of this picture. This is called Dow Vallis. It's a large spring alcove, and it represents a place where water erupted from the subsurface of the flanks of this volcano and flowed off towards the south, towards a large lowlands located off the lower edge of this picture. This Dow Vallis could in many ways be interestingly analogous to Warner Valley, and that is a valley located along the flanks of the volcano that has become a focal point for water coming to the surface and flowing away downhill. And so in many ways we see features now on Mars that are perhaps very analogous to what we see in Lassen Volcanic Park. And as a result, the observations that we make in Lassen could be very relevant to helping us understand how we might explore similar places on Mars, with an idea of perhaps searching for evidence of life on Mars in places where the ability of the environment to support life might have been very promising. And this is, of course, then how we connect our work in Lassen Park to our future planning of missions to Mars to search for evidence of another example of life in our solar system. The end.